Welcome back. In the last section, we tried to classify handwritten images with normal artificial neural networks and reached a very limited accuracy. While we got a decent accuracy from this network, we realized that the accuracy would plateau at a certain point, and attempting to improve it beyond that point would have resulted in overfitting of our data. Therefore, we are going to take a new direction towards a different type of neural network, namely the convolutional neural network. Convolutional neural networks have changed the way we classify images, because they are very effective at recognizing useful patterns within the images by understanding that spatial structure of the inputs is relevant. While typical neural networks ignore the spatial relevance of pixels, such as pixels being closer together versus pixels that are further apart, convolutional networks are designed to use the spatial data for their benefit. Convolutional networks also require a lower quantity of parameters when compared to artificial neural networks. Here's a simple example from GitHub of a convolutional network that's classifying the image of a cat into its appropriate class. We'll go through convolution, pooling, and fully connected layers in subsequent videos, but one obvious similarity between a convolutional neural network and a regular neural network is the input layer. Another similarity is the fully connected layer, which essentially is just a multi-layer perceptron parameterized by weights and bias values that make use of the softmax activation function in the output layer, which, after many convolutions, outputs the probabilities of the image belonging to some class. Appropriately, the highest probability belongs to the image being a cat. Convolutional neural networks, their name stems from the convolution operation that occurs in its network, which we'll discuss in subsequent videos. But ultimately, convolutional neural networks are known to process data that has a known grid-like topology, and as such, we'll be using convolutional neural networks to solve image-driven pattern recognition tasks. Which makes sense, since as previously seen in the computer vision section, we know that images can be read as a grid of pixels. In the case of grayscale images, which once again is what we'll be dealing with in this section, they consist of a two-dimensional array of pixels, each pixel value ranging from 0 to 255, depending on the pixel intensity. The darker the pixel, the higher its pixel intensity value, as clearly shown in the following representation. That being said, image recognition is no easy task, and regular deep neural networks will often struggle with the computational complexity required to compute image data. The reason why we were able to do it with some accuracy in the last section is because the MNIST image datasets have a relatively small 28 by 28 dimensionality. In this case, these images were manageable by the feed-forward neural network. The problem being this isn't scalable to much larger images, or even colored images with multiple channels. Going back to our previous example, a single node in the first hidden layer, a single neuron, was parameterized by 784 adjustable weights, as it's connected to 784 input nodes. However, let's imagine that we're dealing with a much larger colored RGB image, 72 pixels by 72. 72 times 72 corresponds to 5,184 pixels, and since we're dealing with a 3-channel colored image, with each pixel corresponding to 3 pixel intensity values, results in 15,552 pixel intensities. And thus, 15,552 weights parameterizing each node in the first hidden layer, whereas with MNIST, there was only 784. Our network would need to be a lot larger than the one we used for the normalized MNIST dataset images, as we're dealing with a much higher computational complexity. We would have to increase the number of nodes and hidden layers in the neural network. The only problem being, due to the sheer size, we would not have enough computational power to train them, whereas with convolutional neural networks, it makes image processing computationally manageable. We'll see examples of this later on. Another drawback of using regular neural networks was overfitting, which occurs when a model tailors itself very closely to the data that it has been trained on, reducing its ability to pinpoint generalized features of test data sets that it hasn't seen before. Whereas with convolutional neural networks, we can make use of what's called pooling layers, which will act to continuously reduce the number of parameters and computations in the network. We'll talk more about pooling layers and the architecture of a convolutional neural network in the near future. But to conclude this lesson, it's important to note that regular artificial neural networks are very limited in their capacity to classify images, which is why we use convolutional networks in the field of pattern recognition within images. Let's talk more about the architecture of a convolutional neural network in the next video.